So today we'll be looking at another. Today the next lecture is going to be about dynamic programming, and then we'll move on to other things. We'll go for flows. So there are two more lectures where we'll be doing dynamic programming, and today we'll be looking at another very important application of dynamic programming, which is sequence alignment. So, what is sequence alignment? So the question is, question occurs like naturally in many contexts. So I'm still not feeling well. Like yesterday I came back and then from some duty, and then I got a cold, so I had to cancel yesterday's combinatorics class. So I hope it's not too bad today, but let's see. So yeah, I might I'm not feeling the best. That's all. So anyway, so sequence alignment occurs like it is encountered quite naturally in like different domains. So one of them is like for example, spelling suggestions. So when we say like any word we type like whatever alignment, for example, if we type Google, if I we write like this alignment, and I ask Google that, Google will say, "Did you mean alignment?" And so the question is that how does it find out? How do we search for similar looking words, or what is the way that they figure out that okay, maybe this is the word that we mean, right? So what can be a good way to model this phenomena that okay, this is something that we might have meant, right? And the way to do that is looking for similarity between strings. Again, like this is still not very formal. And now what do we mean by similarity between strings? That somehow like they can be lined up with each other. So for example, let's look at one example of lining up, that we write this word letter by letter that we have typed. So let's say, okay, and we look at the correct letter, and okay, let's say A, L, and then there is nothing like to, maybe we should not add anything here, right? So now we have sort of aligned it more or less. There are these two places where it's not like very perfectly aligned, right? But other places it has aligned. So what is this now? What is this thing? This. Okay. So this is represents a gap, right? And this we do that when a letter in a word does not have uh, a match from the other word. Let's say again, like I'm using very crude terminology, right? But even after this these gaps, everything is not perfectly matched, right? So here you'll see that this is still not perfect. So even after gaps, things might not be perfectly matched. Okay. So here we have the example that I is mapped to E. I is matched with E, which is not like, very perfect. Good. But this might give us an idea for how do we now model this problem, that this similarity problem. Okay. So if we determine the similarity, if we say that it is determined by these two quantities, right? The number of gaps and mismatches. Right. But then, like, how do you compare these? These are two very different kind of things. Like, if you match an E with an I, maybe it is not so bad. But if you match an N with a P, that might look, worse than, an I with an E and so on. Right? For example, like, the same thing here, we had one gap and one mismatch, and then I can also do what I can do is, okay, let me do here. And then what I can do is here I can suppose that. So now there is no mismatch. What I have put, basically this I and D, I did not want to align them together. So I have put one gap in this, one gap in this, and aligned them with the gap. So now I've got three gaps basically and no mismatches for the same spelling that I had earlier. So this is one gap, one mismatch. Three gaps, no mismatches. So which one we should prefer, right? That becomes a question. Yeah. And there's another thing that, in English language words, it might be easier to find, these alignments or, whether things are aligning or not. But in binary strings, it might not be that obvious. For example, there are these two strings, let's say 1, 0, 0, 1, 1, 0, 0, 0, 0, 1, 1, 0, and 1, 0, 1, 0, 1, 1, 1, 0, 0, 0, 0, 0, 0, 1, 0. So do these two strings like look very different or very similar? Like, it's not, at least to me, it's not very obvious that if somebody asks me like, whether they're similar or not. And surprisingly, they are similar to each other within like, gap of four. I mean, total thing four. So if you just put them together now, so let me write it down. 1, 0, 0, 0, 1, 1, gap, gap, 0, 0, 0, 0, 1, 0. This is the first string, and the second string is basically 1, 0, 1, 0, 1, 1, 1, 0, 0, 0, 0, 1, 0. Right. So now there are just four mismatches. Basically, one mismatch and four gaps. And apart from that, everything is matched. So, I mean, while looking at the strings, I don't think I can guess that whether they are very similar or not or whatever. So in binary strings and all, it becomes slightly like, harder to see by, by just looking at the word. And the problem also occurs in molecular biology. And what happens? Again, like, we had talked about the DNA sequence, and it has something called chromosomes. And what are chromosomes? Chromosomes are basically large strings of, again, ACTG, the bases, right? And now you have, suppose you know that, and this determines, the properties of some organism. Like, even Down syndrome and all, can be traced back. Yeah.
So it won't matter much, but in the binary string example, if you remove the last two gaps, it would be better, right?
So say again, Shravan.
If we remove the last two gaps, so
Yeah.
it would just add one mismatch and we would reduce two gaps.
Yeah. So we'll come to that. So we have not yet defined that whether we should give more importance to mismatch or to gaps and so on. We'll come to that. Okay. Let me just finish this what I'm doing right now, and
Okay.
we'll address that question. Okay.
Yeah.
Okay, so yeah, what I was saying that there are these large strings which are made of these bases ACTG, and they determine the property of organisms. Like even for humans, I was saying that there is a sequence in our gene, in our DNA that if you see that it's there, then it might tell very high likelihood of, for example, Down syndrome in the kid, and such things were discussed very fiercely whether then people should go for some measures to correct that after they have found out or to abort them if they have found out such a thing. So anyway, so these issues are there, but the point is that such a thing, a string of letters inside the DNA can determine some property of the organism. Now, what about a similar string in some other organism or a similar organism? So that might, make it likely that the other organism might have a similar property. So the book gives example of bacteria, that a bacteria has some DNA sequence which encodes a toxin, that because of that the bacteria ends up having a toxin, and then another bacteria has a very similar DNA sequence, I mean a part of the DNA sequence which in the first bacteria denotes existence of a toxin. Then the scientists can sort of guess that okay, maybe this is a similar toxin, or which is present in this bacteria. This is the part of the genome of the DNA that is responsible for that toxin in this other bacteria. So this is one other application of this particular problem, right? That you look at the DNA of one organism and then see that what it does in the organism and see if something similar is there in the other. Right? Okay, so now the question, as Shravan was asking, that how do we how do we define this? How do we define the problem? How to define this similarity? So we have done like some work. So we have these two parameters. We have these gaps, and we have these mismatches, right? So now let's define this in terms. So the idea is that for gaps, let's have a fixed penalty. And for mismatches, let's see which letters are being mismatched. Right? And then using these two, now like, these two will become the parameters, and then using that, we'll define the problem. Right? So let's try to define the problem, or the idea of the similarity, the way we are saying it. So now let's get a bit more formal, and let's say that let X be the first string of size M. The strings might not be of the same size, like we saw, right? Might be different sizes. Okay, and again, let 1, 2 to M be positions in X. And 1, 2 to N be positions in Y. Right? So now what do we want to have? Now again, we want to have a matching sort of thing, like we did in the last, in the RNA substructure problem, that we want to match these somehow, right? So now the aim is to, okay, so aim will come to later. So let's say a matching of the form, like let's say xi yj, right? A set of xi yj's is an alignment right, if there are no crossing pairs. And what do we mean by crossing pairs? So I, j, and I prime, j prime are crossing pairs. Or let's say, so let's define non-crossing pairs. So I, j, and I prime, j prime are non-crossing if I less than I prime implies j less than j prime. Right? That it is not the case that, so you have these, strings, so you don't want a situation, so this is y, this is x. You don't want a situation where, something gets aligned like this. That you get, this is xi, this is xi prime, this is yi, this is yi prime, and you are putting, okay, no, yj, yj prime. Sorry. So suppose you match xi with, okay, xi with yj and xi prime with yj prime, and suppose this happens that, I is less than I prime, but j prime is less than j, so this is not allowed. So again, this is similar to, the non-crossing condition that we had in the RNA substructure problem, right? So let's another let's look at an example. So suppose we have two words, stop, and here we put the gap, and tops. right? So what is an alignment now for these corresponding to what I have written? Alignment is a set of edges or a matching. So what is the alignment? Set of pairs. So what is going to be the set of pairs here? So this is 1, 2, 3, 4, 0, 4, and again, like this is no position in X, and this is 1, 2, 3, 4 for Y. So what is going to be the alignment? I mean, why did I say 1, 2, 3, 4 here? Because X is equal to stop and Y is equal to tops. Right? So what is the alignment here? Tell, like, please, somebody speak up that what is going to be the alignment? We have defined the alignment to be what? A matching of certain type. So for this example, what is going to be the alignment? Corresponding to this particular thing that I have written here.
1, 4, and 2, 1 and 3, 2 and
4 is not going to be there now, Ayush, right? Because it is now just the non-crossing pairs.
okay, just the non-crossing. Okay.
Yeah, exactly. Because an alignment is a matching of the form where there are no crossing pairs, right?
Okay. Now.
Yeah. So now.
2, 1 and 3, 2 and 4, 3.
Yeah, 3, 2 and 4, 3. Is that clear to everybody with this example? That what is the kind of matching that we are looking for?
Sir, what if there are multiple matchings? So in this case, 2, 4 also can be formed.
Definitely. There can be other ways to align these things. But the thing is that for this particular alignment I was asking, which I have drawn here, if you align slightly differently, then you will get a different matching. And now we have to figure out some matching among those, and that I have not yet come to. Now we'll define the cost of a matching, and then we'll come to that how we do that. Okay.
So in the definition of matching, then should the pair should be I comma j and not xi comma yj, right?
Yes, you are right. Thank you.
And xi should be equal to yj also.
No, that is not necessarily the case, because if you remember this alignment thing where we had matched here, right? So this is also going to be a matching pair. Like here, this one, right? We don't want to leave this. Okay. So we'll come to that how we deal with it. Okay. So yeah, this is a good point that in this one, we did not have the same matching pair. So suppose it was not tops, but toes, suppose. And still we want to align it like this. So we'll get the same alignment, even though this one is not same. Okay. So the alignment or the set of things does not mean that both of them are going to be the same. It only have to satisfy this property that this is a matching and there are no crossing pairs. That's it. Okay. Any other question?
Sir, can you repeat what is a gap?
What is a gap? So gap was a very crude thing that we had defined. Now we don't really have in this definition we don't have anything for a gap. Gap was something defined earlier, just to look at things that okay, maybe some things might not match. Like you repeated a letter here, so there might not be a proper match there in the other string for that. Okay. So that is what a gap was, and we wanted to count gaps as as something bad. We should not have too many gaps also, and we should not have mismatches also. So here these things are gaps, but now they are implicit in the definition of a matching. So there are gaps here, This is a gap that this guy is not matched with anything. This is a gap. This guy is not matched with anything. And this is a mismatch. Okay? Nikhil?
Yes.
Yeah. And now I'll define how we try to minimize this thing. So let's first define cost of an alignment. Okay. So now this is so now the gap penalty. First, every time there is a gap, something that is not matched with any string. So basically now x1, there is no one here in the first position in the matching, right? So one is not matched. One of x. So basically x1 is not matched with anything. So that is a gap basically. Similarly, y4 is not matched, right? So for every position of x or y that is not matched, we incur a penalty of delta, right? So this is some parameter and we call this gap penalty. So every time that happens, we add delta penalty, right? And now for each pair PQ, in the alphabet, there is a mismatch cost alpha PQ, right, for matching P with Q. So for each xi, yi in the M, we have cost, we incur cost alpha xi, yi. Okay, let's ij in M, yj. So there is one thing that usually we'll have alpha like pp to be 0. Like the same letter with the same letter, we should put it 0 because there is no mismatch there, but this is not necessary. I mean, you can put some it does not really affect anything. Right? And now total cost of a matching is sum of gap penalty, gap penalties, let's say, and mismatching cost. Right? So basically, this delta and this alpha, whatever PQ, are external parameters that can be tweaked. According to the application. But they remain fixed for for one particular purpose. An algorithm. Right? And now what do we want? So now we have defined like, that what is an alignment. We have defined cost of an alignment. And now what is the question? Given x is equal to x1 to xm, y is equal to y1 to yn, find an alignment of minimum cost. Okay. So is there a question about the cost of the alignment part? How do we define the cost? And then about the aim of the algorithm, that we want to find an alignment of minimum cost. Is there any question? No?
Sir, is alpha PQ is same for every pair PQ if P is not
No.
equal to Q?
No, that is why I have written PQ, right? Otherwise, I'll just put like, some alpha for every mismatch, right? So that depends on the letters. That is why I'm writing alpha, xi, yj, and so on.
If there are different, how can we find minimum cost?
Because once you fix an alignment, the cost of that alignment gets fixed. Because so whatever pair you have, so you have an m, right? M is equal to some 1 2 3 4 whatever 5 8 so on, right? Now so 1 2 means there is a particular xi, and that means there is a particular x1, and there is a particular y2. So these two are fixed now, that this is x1, this is y2, and they have a cost alpha, whatever this letter is at x1 and whatever this letter is at y2. And for this particular m, for this particular alignment, you have to add this cost. So this is going to be plus whatever, So you don't have 1. So for you that you have delta for y1, and then you have whatever. You add this alpha, this, plus you have delta for x2 maybe, plus you have alpha x3, y4, plus and so on, right? Again, some deltas for whatever is missing in both of them. So this is fixed now, right? This is the cost of this particular matching, this particular alignment. And now you have to find the minimum cost alignment over. So for now, the cost becomes fixed for one alignment, and you have to find the minimum cost over all alignments. So I don't see why the mismatch has to be same for every 2 letters in the alphabet. Okay.
Okay, sir.
Yeah. Good. So. Okay, so now this is the question that we want to find an alignment of minimum cost between these two words or these two strings. So how do we go about it? How do we design an algorithm? Okay, so again, now let's look at x is equal to x1 to xm and y is equal to y1 to yn. And let's again try to look at these last guys, because that's how we had been looking at, trying to get a smaller subproblem and so on. So let m be an optimal solution. And let's again look at, and again we have this concept of opt ij. So, optimum solution for whatever x and y. And again we have this, like always, we have opt ij will denote an optimum solution for Cost of an optimum solution for x1 to xi and y1 to yj. So this is what opt ij is for. So let M be an optimal solution for x and y. And now again we are looking at going to look at the two cases. So case one is either xm yn belong m comma n belongs to n. And in which case, now we get the easy reference. What do we get? Opt mn is equal to, in terms of smaller subproblems, okay, so let's say anyone, please. So now we want to write opt mn in terms of smaller subproblems, solution to smaller subproblems. What is it going to be?
Sir, we can have three possibilities. First, that the last one will be a gap, in that it will be m-1 comma n.
No. Wait. Rishabh, mn is in m. So we are talking about the case when mn is in m. That means it is not a gap. They are being matched. xm is being matched to yn by this particular alignment.
So then we can have m-1, n-1, and we can attach the penalty that alpha m comma m.
Exactly. So we have alpha xm comma xm yn plus opt of m-1 comma n-1. Right. So this is the first case. Any problem with this? Because the last one is matched. Now now you find the optimum solution for the previous one and then match these guys with that. Case 2. Case 2 is mn is not in m. Now it's not that clear that mn is not in m, then what do we do? But then there is, as Rishabh was pointing out, even in the first case, that now it will be that either xm or yn is not going to be matched. And why this happens? Reason? So what is case 2 saying? Case 2 is saying that suppose mn is not in m, so xm is not matched to yn, right? Then either both of them are not matched, nothing to show. But why one of them is not going to be matched? Like how do we
Cross.
Consider that if xm is matched, so it would be matched to something from 1 to n-1. So n cannot be matched to something.
Why?
N has to be matched to something above, higher than n, and we don't have anything higher than n.
for it? Like,
No crossing.
Yeah.
We don't want crossings.
Yeah. Non-crossing property that we have defined. Right. So one of xm or yn is not going to be matched. Again, like similarly, you can apply for yn. That suppose yn is matched to something and not to xm, then xm cannot be matched to anything. Right. Again, because of non-crossing property. Okay. So now let's go to these two cases. So case 2.1. Let's say xm is not matched. And then what is going to be the opt? Okay.
Penalty plus
Yeah.
penalty delta
Delta plus
opt of
mm-hmm.
m-1 comma n.
N. Right. So why this happened? Because now you have this string. Xm is not matched. Maybe y is matched or y is also not matched. We don't know. But xm is not matched. We know that. So you find the opt of the remaining part and then add a penalty for xm that xm is not going to be matched. So this is the penalty for XM. Case 2.2, Yn is not matched. Then we get opt m comma n is equal to delta plus. What is this going to be? When Yn is not matched.
Opt
M
m
comma n
comma n
minus
minus 1.
M comma n minus 1. Right? Because again, the same thing gets applied to Yn, and now Yn is not matched. So you find the optimum way to solve the previous problem, and then this is it, right? And that's it then. That basically now you apply this to any general ij instead of, so this we had applied just to mn, but this you can apply to now any general ij, right? For I whatever greater than 1, j greater than 1. Now I'm going to write directly the recurrence that opt I comma j is equal to minimum of these three quantities, right? Alpha xi yi plus of I minus 1 j minus 1. So this is the case when they get matched to each other. Then delta plus of I minus 1 comma j comma delta plus of I comma j minus 1. Right? And when can we say that ij is part of an optimum solution? From the above recurrence?
The first two.
When the minimum is, let's say, if and only if minimum is achieved by the first value. By whatever, alpha xi yi plus of I minus 1 j minus 1, right? So if this is actually the minimum, then xi yi is going to be in the optimum, which is very clear that is how we had been doing earlier, right? So how many subproblems does it make? How many subproblems do we have?
Order Mn.
Order mn. And what is the final subproblem that we want to that will give us the solution? Opt of 1 comma sorry m comma. Right? And there is another thing that we need to initialize things. So what is going to be the initialization? That opt I comma 0 or opt 0 comma I, what is it going to be? If you have an I length string and a 0 length
I
string,
delta.
I delta. Because those I of them are going to remain unmatched. So you have to incur penalty of delta for each of them. So this becomes I delta. Okay, good. So that's it now. Now we have the algorithm. If I have the algorithm here. Okay, I don't have the algorithm here for some reason. Why I don't have that? Okay, but this gives you the algorithm essentially. It's very strange. Okay, I do have it at the end. Oh. Just a minute. Is there a question in the, just hold on. Yeah, in this much time I could have typed it, but okay, fine. All right, so is there a question in the chat? So is there a question in the chat? Because I can't seem to find it for some reason. I'm not able to access chat. Okay, so it was here. Why can't we both be unmatched? Less than unfamiliar. Okay, so I hope that that got solved. Okay, all right. So we are still in lecture 4, it seems. I didn't rename it. Why am I keeping it? Okay, so I tried to do this, but it did not happen. So do it. Okay, so let me just write it down. So what is the algorithm? It's alignment. Let's say X, Y, and then you have this array A 0 to M, 0 to N. Right? This is your two-dimensional matrix, array that where you are going to do, and then initialize A 0 comma j is equal to j delta for all j, and whatever A I comma 0 is equal to I delta for all I, so on. And now for actual algorithm, j is equal to, you start from j is equal to 1 to n, let's say, then you go for I is equal to 1 to n, m, you just find the of ij using the recurrence, then you end for return a or of aij you fill accordingly, return a. So this is what you do, and every time whenever you are computing I comma j, aij, what are you going to use? You are going to use either a I minus 1 comma j that you have computed already because I minus 1 you have gone through, or you are going to use a I minus 1 comma j, or you are going to use a I comma j minus 1 that also you have computed because you are for that particular I you have computed the j minus 1, so that is also you have computed, or a I minus 1 j minus 1 again you have computed. And now using the recurrence, how much time does the computing things from the recurrence takes? Time taken for some ij. What is the time? Order 1, right? Because you just access these 3 values and then just find the minimum. So this is the first value, second value, third value, and you just find the minimum of these 3, and that can be done in order 1 time, and you can just access them. So total time is order mn, right? And the space also is order mn because you have this table, but then again you are just accessing one before. So just for the finding the value of the optimum, you can sure. So for modifying this version now, sorry, modifying this version, I just read that and then. I mean, find the optimum alignment, I mean. And actually in less space, like in order whatever m space, or let's say, yeah, order m space, or m plus n, let's say, because if the difference is too much, then you can find the opt, but maybe not find the optimum alignment. That is not so easy, but not alignment. And now book has an algorithm for how to find the alignment in order n plus n space. And that you should read on your own. This is a very nice application of divide and conquer for space. But how can you save space by using divide and conquer? Actually, the time is going to be the same, exactly the same, order mn, but you can save on space by using only order m plus n space. So that you should, I think, read on your own. That I'm not going to cover. I would rather go for this thing, shortest paths, and then finish dynamic programming in the lecture, and then we'll go to the other lecture.
So can it not be done in order minimum of m comma n space?
Same.
Order minimum of m comma n and not m plus n.
How?
Like we'll just keep one array of the previous row, and because in the current row we will have values of the previous column anyways. So we need value of previous row and previous column only, right?
In the current row, we'll have.
Like in the current row, we will keep filling values linearly, right? So we will anyways have values of the previous column.
Okay.
In the current row.
Yes.
And we will store one row above. That is, we will store I minus 1.
Okay.
So we have I minus 1j, we have I minus 1j minus 1. And while filling I, we have I comma j minus 1 as well.
Okay, yes. So it can be done even in minimum of mn space is what you're saying, just for finding the optimum. Using what feature? Yeah.
Yeah.
That seems correct, yes. Good. Yep. So that is fine, and yeah. So this you don't, you might not actually need order m plus n. You might do in minimum of m comma n, as someone is suggesting, and that is correct. And but yeah, so doing that in order m plus n space, or then you can think whether it can be done in minimum of m comma n space and so on, and whether these things still translate to finding the alignment or not. So that you should explore on your own from the book. So it has a very nice exposition about these things and how this problem relates to shortest path problem in a special kind of graph and so on. So I would urge you to read that up. And yeah, so that's all for today. Any questions about the algorithm? Any other question? Like how we do this? So algorithm is just basically just following the rectangles. Okay, so if not, then we'll meet on Thursday and we'll do shortest path. Okay, with negative weights and so on. We'll see what are the recommendations. Okay. So thank you for coming today and see you on Thursday. Thank you.